Good morning, Cisco Cohort 2. So I've got 9 o'clock and we're going to go ahead and start. And on today's schedule, we're going to be covering Module 3, which is about protocols and models. And before I get started, I've got this just in from the Cisco newsroom. There's going to be a Texas Netacad Career Fair webinar on April the 15th. And if you go to my TCC Blackboard and go to the very last link, I just added this recently, click on that. And then when you click on the link, it'll open up this PDF file that you can see what's going on with this. And there's a link you can link on here to register to get to go to this online webinar type thing. So this is going to be a great event. This is a repeating event that Cisco has been doing for quite a while now. That is, these are jobs hiring companies in the Dallas-Fort Worth area. They're going to talk about the jobs market for people that have CCNA skills, CCNA certification in the Dallas-Fort Worth area. And it's a good way to gauge your what's going on in the Cisco world and see what real people are actually hiring on the events. We typically have people that are actually hired as a result of attending these events. Okay, so let's see now. So I'm going to go now and we're going to go to start to do the slideshow. So I will stop sharing. Wait a minute, I could just be able to do this. If I go there and go here and share, choose this, share this, choose this. Oh, good, it did it. So Module 3, protocols and models. And what we're going to look at in this particular course for today, in this particular objectives for today, we're going to talk about this concept of rules to be able to communicate over the wires, over the network wiring. We'll look at some protocols. Why do we have to use them? There's all those protocols. They're so confusing. These protocol suites, OSI and TCP IP, oh my goodness. And then we'll look at some standards organizations, a bunch of, basically a bunch of professionals, industry professional technicians and engineers that stayed up late one night and made up all these standards that makes the internet work today. Then we'll look at our two common reference models, the TCP IP reference model, Department of Defense model, and the OSI 7-layer model, and how we use them in the process of education, teaching networking, and also how they're used in industry. And then we're going to look at this concept of data encapsulation. How does that little bit, a chunk of data, like that thing you're sending to the printer, or that page from that web link that you click, how does that get encapsulated in packets and sent back, and where you can see it on your web browser screen? And the last thing is a data access, how do local hosts access resources on the network. So let's get going with this and look at the rules. So let's look at some concepts here. There always has to be a source sender of information. So like when you send a ping request, you type ping, and when you press the enter key, you start the flow of information going, and you eventually send out this echo request signal that you want some other computer to send back an echo reply so you can prove that you have network layer connectivity. So there has to be a destination. You're pinging some destination address. And then there has to be, connecting these two devices together, the sender and the receiver, some sort of channel, some sort of media that connects them together. It could be as simple as a single Ethernet cable between two computers, or a single Wi-Fi connection between two computers. Or it could be as complex as 10 or 15 routers and different internet service providers between the web link you clicked on and the web server that sends that image back to you. More complex communication channels. So protocols are how we do things in a series of progression of things. It's the rules that communication take place. And it's going to depend on the protocol. If you pick up the phone, your phone rings and you say hello, and the other person says, "Is Mr. Smith there?" And you say, "This is Mr. Smith speaking. What do you want?" You're going through a protocol of establishing communication, establishing that both parties are the two parties that need to talk to each other, and they're willing and ready and able to actually exchange information with each other. So the same thing with computers. We're going to break things up into packets, this little envelope icon that's floating around over here. And we're going to break things into as many packets as it takes to get them into reasonable sized chunks. And then we'll send these back and forth to from one device to another device. So we all have agreed upon rules when we talk on the phone or send printed paper back and forth. The first message here is not formatted in the correct fashion. It's got different languages, and the first character is not capitalized like sentences should be. And when you look at the second block of information, it's formatted properly. It's all in the English language. It's formatted properly, and every first word starts with the capitalized letter and so forth. So this is a rule for how we communicate with each other. We can be unclear, or we can use the rules and have a clear communication. So we have to establish for the sender and the receiver, the source and the destination. We have to agree upon a common language and grammar. We have to agree upon how we're going to send our words back and forth to each other, the speed and timing of delivery. And then we have to have some method of acknowledgement that we received the message. So when we're talking about network protocols, this act of taking some upper layer data, like an email message or a request to receive a web page, and we want to somehow get it to the server machine so he can transmit the email or send that web page I requested back to me so I can read it. So we have such topics here as how do we encode the message? Well, for example, how do we encode letters of the alphabet? Well, there's an ASCII character code for doing things like that. We have to agree upon that. Message formatting and encapsulation. How are we going to, when we have to have the text of the message, the commands have to be properly formatted for that programming language to understand it. So an HTML formatted request for a web server to send you a web page back would be completely different formatting than when you click send on your email and you're transmitting an email to an email server. They use different formatics. What size is the message allowed to be? For example, we're going to see when we talk about the data link layer Ethernet later on that Ethernet can hold up to about 1,500 characters of data, no more than that. If you have more data than that, you have to break it up into separate chunks. What is the timing of the message? Can we receive it successfully and process it? And what are the delivery options of what should we do if there's a problem? So let's take the message and encode it. Let's take some text message and convert it into ASCII character code. Let's take a picture and let's convert it into a JPEG code. Let's take a movie or a television show or a moving action with sound, and let's encode it to like an MPEG-4 format so we can move it from one device to another device. So I encode that text message in ASCII and send it to your machine. Your machine will see the binary ASCII codes for the characters of the letters I sent, and they'll show you the proper text that I was trying to send to you. They'll decode that information when the receiving machine receives that string of code. When we send something in the mail, we have this envelope format that we have. We take a piece of paper, and on the paper we write who we're sending it to and who we are, and we send the little message. We fold that paper up, put an envelope, have to put a stamp on it, they won't send it. And on the outside of the envelope, we put our complete return address. That's the source of the message. And then we have the recipient's complete address. That's the destination address. So it's a specific type of a way we have to arrange things to get this mail system to work, the protocols and the rules of the mail system. So when we send stuff with computer data over packets, we have to use different formats in the same sort of a way. So on the right, we have this schematic diagram of how do we put together a network packet. So the network packet has to have things like what's the address that this packet is coming from, what's the destination address to where this packet is going, things of that nature. So it's very similar in concept to sending mail, piece of paper, sending mail through the mail system. We have to divide something into a little paper size, one page piece of paper size chunks of data, and then send them from one point to the other. Now, a message that's too big can't be sent across the network. I mentioned the Ethernet, which is the most commonly used type of sending data back and forth between computers, has a limitation of 1,500 characters per chunk of data. If you have 3,000 characters, you have to use two chunks, two Ethernet frames to send it. And eventually, all these packets and frames have got to be transmitted as electricity, bits representing ones and zeros, flashes of light representing ones and zeros. And they all have to be interpreted and received properly by the other parties so that they mean the same sort of thing. So it has to be appropriate for the medium. So flow control is something that if I want to send you 1,000,000 characters of information, say it's a Microsoft Service Pack 1 update for your Windows 10 installation, and it needs to be a gigabyte of data, and I need to send that data to your machine. Well, I'm going to send a few bits of it, a few chunks of it, and I'm going to wait for your machine to say, oh, I got that first part, okay, send me the second part. That's flow control. That's so that that's a positive acknowledgement and retransmission so that the two machines can make sure that they successfully send that whole chunk of data, no matter how long it is, from one device to another device. Now, what if the device stops answering my messages? We have to have a response timeout, which means, well, for example, in the TCP protocol, which is we'll look at in a later chapter, which is used to positively transmit data. If he fails to hear acknowledgments back from his other workstation that he's transmitting to, after about 100 seconds or so, he's going to say, well, you timed out. You must have crashed or something, and he'll give up. Now, this third thing, access method. When can you send a message? We'll look at this more in the data link chapters. But for example, Ethernet has a method of he can send whenever he feels like it. He's just supposed to listen first. So I call this the Three Stooges poking each other's eyes out protocol. Just poke a message whenever you feel like it. But you might poke somebody's eye out if you didn't listen first. Three different types of ways that we can transmit a chunk of data, like a packet or frame, between different devices in the network. The first method is called unicast. The unicast is 1-to-1. So when I'm pinging your workstation, I'm the source device, you're the destination device, that's a 1-to-1 thing. It's going to be between you and me, and no one else is going to care or listen to that communication whatsoever. Hold on, I'm checking attendance here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, I think I'm okay. So a vast majority of stuff that's sent in networking is unicast. Like when you click on a web link on a web server, he sends you back the web page that corresponded to that link you clicked on. That's unicast. That's between you and him. You take turns being receivers and transmitters, sources and destinations, but it's a unicast message between you two guys. It's like a private telephone call. I pick up the telephone call and I call you, and just you and me hear the stuff. Multicast is one to many, not all. Now let me skip multicast for a second and go to broadcast, because broadcast is, I'm going to use the example of a broadcast message is if I want to send out something and everyone needs to hear it. And a multicast message is one to a group of people, not all of them. So for example, when you were in elementary school and the principal came on in the morning and push the button where he was talking to all the classrooms and he said, everybody stand for the Pledge of Allegiance. That's a broadcast message. From that principal's microphone to everybody's speaker, that message is being broadcasted throughout the entire building. So that was of interest to the entire building. But what if you want to send a multicast message and it's only of interest to a particular group of people? So let's say that the lady at the attendance office at the front desk comes on the intercom and just goes to your classroom that you're in, just turns on your speaker and says, Mrs. Smith, would you send John Doe to the front office? He has a doctor's appointment. That was sent to a group of people, a multicast. The group was just that one classroom that had the people that we had to find that student and send them out. So that's the difference between broadcast and multicast, just like the principal's machine. So broadcasts are used in IP version 4 networks, as it says down here. In IP version 6, they have the exact same physical function, but they changed the name of it so you could feel better about it. But we'll talk about that when we get to network addressing. Okay, let's look at some protocols. So protocols are things that we can have in both hardware and software. We can have a computer software that runs on something. We can also have firmware or hardware that does something, like a network interface card. And protocols have their own rules and the way that everything must be formatted and their particular functions. So if we look at the chart here, the protocol type, pencil on. Yeah, we look at the protocol type. So the network communication protocol types, there's several protocols involved in network communication. that allow two end devices, two endpoints, to talk to each other over a network. And then we have some network security protocols that, for example, did you put your correct password in? Otherwise, it's not going to give you access to the network. We can authenticate users. We can encrypt data. So like when you're putting in your social security number or your credit card number to an internet website, no one else can see that data. So we also have some protocols for all those average of 10 or 15 routers that connect you to that web server that you're talking to right now. They have to have a method of figuring the best path for your unique individual communication to go back and forth between them and you. So there's some routing protocols. And then there's a new concept, well, it's not new, it's about the year 2000. They started talking about something called auto-config. We should just be able to plug whatever we have together and it should just start working magically. We shouldn't have to configure anything. So one of the pushes between IP version 6, which started being adopted around 1999-2000, was it should be able to auto-configure itself. So network devices have to use some protocols that all the vendors and manufacturers of these network devices, even if they're different companies, they have to agree upon these protocols to work the same on all of them. Because, for example, I can have a Mac PC, a Mac OS desktop. You can have a Windows desktop. Someone else can have a Linux desktop, and they can all communicate with each other because they're all agreed upon these rules and protocols for communicating messages back and forth. So some functions we have here are, we need to be able to have an exact protocol for identifying the sender and the receiver. For example, we might use a network address, like an IP version 4 network address. We have to have some means of reliability to make sure that we have positive acknowledgement and retransmission of data flowing back and forth to the channel. Any glitches or collisions, anything that happens, it would be retransmitted. Guaranteed delivery of perfect data. We want to make sure that our flow control, make sure that the data can flow as fast as possible, but not overwhelm anything. Think about Amazon on Prime Day. Boy, do they have to have their web servers programmed for flow control, because everybody's hitting them all at once. Get that limited deal that's going to run in 1 hour on this pad. Sequencing. What if data? One of these things about the routing layer is it finds the best path at a particular instant. It might not be the exact same path for the entire document. So the third packet might get there before the second packet. Does that mean your page numbers will be out of order in the report? Well, no, there's a built-in sequencing method that puts everything back in the right order at the receiving workstation, even if they happen to be transmitted out of order. We do want to know if errors have occurred. So we're going to have a method of testing to make sure that no errors have occurred, or if any errors are detected, then we can retransmit the data and recover from that, because we can't have any bits go bad or it might crash everything. And then we need some way of communicating between network applications. For example, the routing protocol process on the router that you're connected to might have to have a specific routing protocol to talk to the routing protocol that the next router is talking to. Let's look at some particular protocols, and we're going to start with a protocol at the very highest layer. It's the very highest layer of communication here. This is something called the application layer, and we're going to use something called hypertext transfer protocol, which is the way the code that is used, the protocol, the rules that are used to transmit web documents that appear when you click on a particular web page. That just takes care of the exact formatting of the text itself of the web page. Now we're going to add another protocol below that called transmission control protocol that makes sure that any errors that occur, that the faulty data is thrown away and the correct data is retransmitted. Make sure that flow control is maintained. If there are, oh yeah, think about that Amazon website again on Prime Day. That one web server at Amazon has got like 100 individual connections coming in to try to buy 100 different products. He's got to manage those individual conversations and not mess up somebody what's up, put what somebody else ordered in your basket, and that would not work. That would guarantee they wouldn't sell anything. So TCP has a protocol for managing multiple transmissions. Below transmission control protocol, we're going to actually take this chunk of TCP data and we're going to put it in a network packet. And that's how we're going to address all of these. When we address the envelopes, we use this individual unit. So when we send our equivalent of letters through the mail, which is network packets to the network, we're going to address them so that they can be determine the best path and they can be sent to the proper destination. Then underneath that, we physically need something to move it all. So the U.S. Mail Postal Service has physical things to move things around, like airplanes and mail trucks and baskets and mailman's leather bags and things of that nature. So the lowest layer, we're going to have something that's actually going to transmit our bits along the network, step by step, from device to device, until they're delivered from the source machine to the destination machine. Okay, some protocol suites are, these are groups of protocols. So we just looked in this last thing that we had an Ethernet protocol, and we had a network layer protocol, and we had a transmission control protocol, and then we had the hypertext transfer protocol, all working at different layers. So protocols work as in the concept that they go from their higher layers and lower layers, and they all are each responsible for doing their own particular part. One does the security, one does the dividing in the packets and so forth. So let's look at the very common protocol suites. The Internet Protocol Suite, or TCP/IP, this was the ARPANET, the original Department of Defense model that was developed back in the 70s. And it turned out to be, it's the protocol of the internet today. It's the actual protocol that we use on the internet today. The exact same protocol. It's called TCP/IP. There's about 10 or 12 protocols that we're interested in from the CCNA level. We abbreviate that, we just call it TCP/IP. There is another, it has a 4-layer protocol. There's a 7-layer protocol. I call it the dreaded, feared, and hated 7-layer OSI reference model that was developed by a bunch of academics and engineers that sat around a table. These are the same people that standardize, the number of threads per inch on a screw and a bolt so that the manufacturing industry can build machines. Okay, that has to be a standard throughout the world, or nothing would fit anything else. It turns out, though, that's a very handy layer for training and education and networking, because it allows us to zoom into one particular function or thing to the exclusion of all the other layers and sort of focus on that and get an idea of what's going on there. Now, a couple of more protocol suites that are not very popular anymore. AppleTalk was a suite that when you bought the first Macintoshes back, it was 1984, 1985, you could plug them together with telephone wire and they would start networking with each other just fine. So you could share, a $5,000 laser printer among 10 Apple desktop PCs using telephone wire. Very easy, just plug them together, no skill required whatsoever. Another was Novell NetWare, which was before Microsoft became interested in networking and the internet became popular. And this was a hot thing that took off really about 1995. That's when Microsoft Windows 95 was released. And that's when Microsoft decided their NT file server print sharing software that they wanted to compete with Novell, because Novell had the market here since about 1980. So they had the market for a good 15 years. It was all Novell network stuff. That was a different set of protocols, very similar to what we use today for TCP/IP in the sense that Portuguese is similar to Spanish, but they're not the same. They do not interoperate with each other. So TCP/IP protocol is the protocol of the internet. So this is where we're going to use, we have something called the application. This is the layer that talks to a program running on your PC like a web browser. You run a web browser and you click on a web link, and it's going to use the hypertext transfer protocol to begin to get your data ready so it can go through the internet. LAN, we talked about LAN and WAN, didn't we? Yeah, we talked about LAN and LAN. Hold on, update my attendance. So it's 1, 2, 3, 4, 5, 6. Okay. So local area networks are networks that are very high speed within a building, like a classroom or a company or your home, Ethernet based. And they also could be Wi-Fi based, like WLAN means wireless LAN, so like Wi-Fi transmissions. These are the most common network access layer protocols that connect things, physically get things connected to the network. TCP/IP is open. It's an open protocol. It's open source. Means that it's not owned by a company. It's not a proprietary thing. Microsoft Windows is a proprietary product. It's owned by Microsoft. You can't get the source code for it. They won't give it to you. It's a trade secret. You don't buy a copy of Windows. You buy a license to use it. They own the product. Now compare that with Linux. Linux is an operating system. It'll do this whole same thing that Microsoft would do, Microsoft Windows would do, but it's open source. The source code is free. They can't charge you for it. They can charge you to support it, like Red Hat. They'll give you the software for free, but they'll charge you for supporting it, and everybody has to have support. So TCP/IP is an open protocol suite, freely available. Any vendor can use it. They don't have to pay any type of license fees. Many home routers, for example, have lines of code from Linux in them to make the home router work properly. So its open standards are supported by the entire manufacturers and vendors, the people that make networking stuff. And then we use a standards organization to kind of put their final touch of authority on it to say this is a good standard, we should use it this way. So let's look at this process. If you're running a web, you're on the right, and you're running a web browser program like Microsoft Internet Explorer or Mozilla Firefox or Chrome or something like that, and you click on a request to a web server, the one on the very left, and he's sending the answer back to you. He's in the process of sending the response. The web page that you clicked on is being in the response being sent back to you. So when you clicked on that, this user data, this is the answer. This is the information, the JPEGs and the text data that forms that page. It corresponds to that page you clicked on. You're going to get that back. But we need to put some extra information around it. I can't just throw a piece of paper in the mailbox. I have to put an envelope, put an address on it, put a stamp on it. So we have to do something like this to make a packet that will be, routed through the network, and they'll find the best path to that web server. So we're going to wrap it in an envelope called TCP, Transmission Control Protocol, and we're going to call that a TCP segment. And if there's more than one chunk of data, we'll have segment number 1 and segment number 2 and segment number 3, however many segments it takes to send that whole chunk of data. And then we're going to put that whole thing into an IP packet, which is close to an envelope that goes into the mail system. It has the address to send it to, it has the address to send it back, the answer to. And then that whole thing has to be, just like an envelope, has to be physically conveyed in a mailman's leather bag, and then in the truck, and then the plane to the other city, and so forth. We have to physically convey this copy of this letter, this packet, through the entire network to get it from one end to the other. And that's what the Ethernet frame is going to do. He's going to actually take that information and transmit it in the form of electricity at the back of that network connection, and then to fiber optic cables or Wi-Fi or whatever it takes to get it connected eventually back to you. So he encapsulates this data. The receiving workstation receives the stream of bits, recognizes it as a valid Ethernet frame, opens up the Ethernet frame and pulls out the IP packet, like the mailman putting the letter out of his leather bag into your mailbox. And then you open up the mail and you see the letter that was in there, and the upper layer user data is shown. So eventually, the Ethernet frame is open, the packet containing the elements of that web page that you clicked on are open and appear to the user in his application program, Internet Explorer, whatever web browser he's using. Nothing complicated about that. Okay, let's look at some standards organizations. There are many standards organizations that centralize or coordinate all this stuff so that they can all work with each other. So it's to the benefit of the manufacturers, the companies, the vendors that make and sell all this stuff, that everything work with everything else. It won't be like 40 or 50 years ago where IBM tape drives would only operate with IBM computers. And if you had a Burroughs computer, you could have to use a Burroughs tape drive and a Burroughs printer. Nothing interoperated with anything else. But everything can operate if everything can operate with everything else, it's better because you can plug anybody's printer into anybody's computer like you can do now. This is good for the industry. It's good for competition. It's good for innovation because new products that will be brought out would have faster performance or faster protocols, and people would buy them. So standards organizations are vendor neutral. Okay, like the Cisco CCNA is not a vendor neutral certification. It's a Cisco certification. A vendor neutral certification might be the Cont TIA A+, which is a break-fix computer knowledge certification where you can fix all different brands of devices. Standards organizations then are vendor neutral. They're not owned or operated by any one particular for-profit corporation that makes stuff. They're typically nonprofit organizations, and they want to keep things open. So like the Linux community is an example of a community that's promoting the use of operating systems that you don't have to license for. You can get the source code for. There are some groups of volunteers, of really smart engineers and technicians, the Internet Society, Architecture Board, the Internet Engineering Task Force, and the Research Task Force have for years been working on all these protocols and make sure they all operate properly, making sure that anybody can use them for free, that nobody can license them or put a patent on them and keep other people from using them without paying a particular fee. That's the Microsoft model, is to license stuff. In the open standards world, we want everybody to use this stuff for free. Now, there are some organizations that these particular IP addresses that you use, you got one from your cable company. The cable company got a whole bank of them from the what I call the name and number authority people, like the Internet Corporation for Assigned Names and Numbers, ICANN, in the United States. The Internet Assigned Numbers Authorities, and all these organizations work worldwide so that you can register for a domain name. If no one else has got it yet, you can get a domain name. If you're a big ISP, you can get a block of IP addresses. If you're a small customer, you probably just lease an IP address from an internet service provider, and you won't directly contact these people. There are some industry associations that are trade organizations to promote the networking industry. Manufacturers like Cisco and Juniper and Arista and all these other people that make networking stuff, that they're interested in communications, networking and telephone company equipment. So the Electronic Industry Association, the Telecommunication Industry Association developed standards. A good example is the EIA TIA 568B. This is that RJ45 connector with 8-position connector that it's a standard in networking today. No matter what type of networking you're using RJ45 plugs. Now, reference models. Here is an example of the OSI model and the TCP model shown side by side. So when we use layered models, let me say right off the outside here, all models are faulty, but some are useful. The TCP/IP model and the OSI model are useful, particularly in training, education for networking, because it allows us to zoom in on one particular issue of one thing that's happening at one point in the network to the exclusion of all other things, and try to learn and comprehend what that's about. For example, if I wanted to talk about, what's happening at the physical layer? Well, really 3 things are happening at the physical layer. We have bits of electricity representing ones and zeros flying through the wire at 10 million bits per second or whatever speed it is. And we are careful to shape the plugs and jacks on both ends of this wire so they can successfully transmit these bits levels representing ones and zeros, binary data, from one device to another device. That's all the physical layer is doing. He doesn't care all whatsoever. He's not concerned with, passwords or IP addresses or segment numbers or how many communications, which communication is this on the 500 that are coming into that web server? He's not concerned with that at all. He's merely concerned with conveying the bits, the ones and zeros back and forth. So we can look at issues like, well, what wire gauge size do we need to use? How do we shape the plugs and jacks so they fit into each other? How do we set the clock circuit up so that it's operating at the proper rate of speed? To the exclusion of all other topics. So in this fashion, we can look at all these individual processes that do take place in networking and look at them individually instead of seeming a bunch of overwhelming stuff that's happening. So here's Here's some benefits here. I like the one at the bottom, a common language to describe networking functions and capabilities. Well, we're teaching and learning networking here. We need a common language to describe all these protocols, all these functions, all these capabilities that are taking place. Prevent technology or capability changes in one layer from affecting other layers above and below. And I'll give the example of that. A network hardware engineer is designing a new Ethernet card that he's going to put in desktop PCs. And there's hundreds of these on the market. So he can make a change in his network card, and you won't have to recompile your copy of Windows 10 or Linux or Mac OS because you're at a different layer. You won't have to wrap a whole new wiring system between all the computers in the universe because you made a change at that data link layer card. So it allows us to zoom in on one layer there, and if we make some change to improve the card electronically, we don't have to change everything else as well. This is good for the business. It's good for the industry, the networking industry. It's good competition. Different products from different vendors will work together with each other, and that's good for business. So here is the 7 layers. The physical layer is the lowest layer. This is the over the wire layer. And here's a mnemonic for memorizing this order. It's starting from 7 and going down to 1. There's a mnemonic sentence for remembering this, and it's all people seem to need data processing. On the way up, if I go from 1 to 7, it's please do not throw sausage pizza away. Some way of memorizing the order of this that they go back and forth. So the application layer is a layer that actually talks to the application layer program, number 7. There's not much concentration on the presentation and session layers, layer 6 and 5. As a matter of fact, we roll those up into 7 in the TCP/I layer. We'll call that the whole application layer. But the presentation layer is, for example, if I wanted to send a graphical image, I could use JPEG. If I wanted to send a music file, I could send an MP3. If I want to send text data, I could use ASCII character codes. How do I represent the data? The session layer is the layer that gives you a unique session. You give the correct password. You have now, if you came into the lab in the classroom, you logged onto our Microsoft Active Directory domain with your proper name and password, and we're going to give you a session on your computer where you can use the VMwares and talk to the rack on the back of the room. Transport layer, that's where TCP lives. That's our positive acknowledgement and retransmission that makes sure that no errors are caught and vanquished and retransmitted, and we get error-free data throughout the entire network. Our network layer is like our envelopes in the mail system. That's going to be IP packets with source and destination addresses on them. And then that's where the software stops and the hardware starts. At the data link layer, we're going to take all of these information from above that was encapsulated and form it in physical electricity or physical spots of light that represent our data, our binary data, our ones and zeros going over our common media, whether that's a network wire or fiber optic cable or radio transmissions through the air. And that's down to our physical layer where we kind of get connections that gives us stuff. We get a physical connection back and forth and actually plug two Ethernet devices together with a physical cable and they can talk to each other. Now, isn't this model nicer? This is more simplistic. The TCP/IP model, the application data is all the data that's being sent to the user plus any encoding, plus any dialog controlling passwords. That's all considered just the application layer in TCP/IP. This is the one we actually use on the internet. Boy, that complex model that those engineers came up with, those academic guys came up with, put a bunch of academics around that table and no one's satisfied until everybody's put their thing into the whole model. That's why the model grew to be so big. So transport layer is reliable end-to-end communication. Internet layer is put everything in a packet, and then that packet will find its way automatically to the right place to be received. Just like when you put a piece of mail in the mailbox, it finds its way to the destination mailbox and appears in that guy's mailbox. And then the network access is the mail bags, the mail trucks, the mail planes, all the things that actually carry. This is the media and intermediary routing devices, routers and switches that actually carry your data from one point to another point and make up the network part of this whole communication. So if we look at the OSI model and the TCP/IP model, the OSI model is more complex because it was designed by a bunch of academics. The TCP/IP model is more like a model that grew and worked, and they used it, actually used it from the 70s onward, and it turned into what we use on the internet today. So the TCP/IP model is commonly, is what we actually run the internet on, but we'll still talk about, in the OSI model, I'll talk about stuff being at the physical layer or the data link layer, and I'm trying to zoom in on one particular concept or function to the exclusion of everything else, so we can take a closer look at that and not concern ourselves with anything else right now but that particular topic, so we can gain an understanding of it. Now, we talked about this concept of data encapsulation. We have two employees here that are trying to talk to the server. They're probably both checking to see how much vacation time they got left on the human resources server, and they can't wait to fill in that time off request. But they can't both transmit their ones and zeros on the wire at the same time. They got to take turns. So a segment of data containing one user's request and a segment of data containing the other user's request will be put in separate packets and sent over the network. That's segmenting the data. That gives it an increase in speed because no one person is tying it up. And if an error occurs and some data is destroyed, we don't have to send the whole thing over again. We can just send the one little packet, the one little segment that had the error. Not everything needs to be retransmitted again. So there's some advantages here. Now, I mentioned the sequencing concept in that if things are arrived out of order, they can be put back in the proper order. In this case, both of these users, purple shirt and green shirt user, their segments are being received in order. But they could have been received out of order, but each little segment has a tag with a number in it, so it can easily be put back. Oh, machines love sorting things. Computers love to sort data. They'll do that all day long. So if anything is arrived out of order, he can very easily sort everything back into the proper order, so that the original data itself, and when it's put back in the right order, it will be in the right form. There won't be any errors in it. It won't be missing anything. No data will be scrambled up. We call these things protocol data units. So I'm going to start with, here's an email. It's too big to be transmitted in one piece. It's going to have to be broken up into smaller pieces. So here's the first piece. Here's the second piece. Here's the third piece. Let's take that first piece and let's make that the first chunk of data that we're going to send. So, and we're going to do this 2 more times. This is the first chunk. We're going to take the first chunk of data. We're going to add some identifying information to it as to telling us this is the first part. And this is for this particular person that's logged into this server, not the 50 others. And then we're going to take that chunk of data and we're going to create the equivalent of putting a piece of paper in the envelope into the mail system. We're going to create a network header with the addressing information, the source and destination, the sender and the recipient. And then we're going to take all that data and actually send it to the Ethernet adapter in the device and create an entire physical Ethernet frame that is a bunch of numbers, a bunch of binary numbers, and that those bits will be sent out to a receiving device. So we call that first chunk of data. Before we did anything to it, that's just this data, it's pure data. When it goes down to the transport layer, TCP, and it gets turned into a numbered segment, that's a segment. The segment will in turn be encapsulated into a network packet and we'll add the addressing information. The packet will be encapsulated in an Ethernet frame. And of course, it will depend on whether it's is this Ethernet device, is it copper attached, RJ45 wire, copper wire, or is it fiber optics, is it Wi-Fi? And eventually those bits will shoot out in the form of electricity through a wire or flashes of light through a copper cable or radio frequency energy through the air in the form of this bit stream to pass to the air. So it's a top-down process. We take the data, then we make it a segment, then we make it bigger and make it a packet, then we make it even bigger and make it an Ethernet frame. And finally, when the finalized Ethernet frame is finally ready to be sent as a bit stream out from the one device to another device and start its journey to the destination device. In the de-encapsulation process, we receive a bunch of bits. Here's all the bits we heard on the wire. Okay, we're going to look at those entire stream of bits and check it out and make sure it looks like a proper Ethernet frame and that it has no errors. If that passes that test, we're going to take out the data portion of that Ethernet frame and send it up to the network layer, and we'll get our IP packet. There's our addressing information. The IP packet will be opened up. They'll pull out the individual segment. Kind of like a segment is up, almost like a page of printed data. It's about the same size. And then that segment of data, that page of data, will be directed to the proper user, and the user will see it on the screen. We will de-encapsulate that data so that the desired data appears on your screen. Now let's look at this concept of data access. We're going to use some addressing, and there's a couple different types of addressing in networking. We've talked so far about network layer addresses, and I've said in this course so far that a network layer address is kind of like a telephone number. There's an area code portion that tells what part of the country you're in, and then there's a 7-digit number that's the individual telephone number in that area of the country. Like 817, that's somewhere in Fort Worth. And then the individual number where there's an individual number in Fort Worth. I want to ring this number and call it. So these are like network layer addresses, network layer source and destination addresses, so the two phone numbers of the people that are talking to each other. There's a physical aspect of it though, because regardless of whether it's a cell phone conversation or packets through a network, we have to have someone physically sending that data back and forth. So you got a cell phone, you're actually running IP version 6 on your cell phone, and your voice is being changed into packets and bits before it's sent to the other phone and making it ring. So in networking, we have this concept. We have source and destination addresses at the data link layer as well. Typically, we call those MAC addresses, physical addresses, burned-in addresses. They're Ethernet addresses. And so that's how each physical device that's in one particular building, for example, they can keep track of your device when it's sent from one point on the network to another point on the network. The equivalent of this in your cell phone would be, did you know that your cell phone has a sort of a built-in hardware, a burned-in hardware unique identity, sometimes called the NAM. This is the unique physical address for your cell phone. You can change your cell phone number, but the physical address of your cell phone will not change. That's how you're really known on their network, is how your physical value. So how are you really known on your computer network? Your computer is really known by its physical address, its MAC address, its burned-in address. That's a data link layer address. That's a 48-bit binary value, and we typically address that with the hexadecimal because that's too many numbers to look at, too many binary numbers to look at once. Now let's look at our layer 3 IP address. You've heard about the 192.168.1.1. These they're called logical addresses because they exist in the software. Now the hardware burn-in address of that NIC card is that 48-bit MAC address, and it can never be changed. But the layer 3 address, I could change that. I could get a different address from the server. I could change the address myself with a static address. So IP packets always contain these two logical addresses. My address, my source address, I'm the original source, and the final destination, what is this IP address? That's going to help all of the devices, all the routers that connect me together, it's usually 10 or 15, to route my packet from packet to packet, route my packet from router to router to make sure that that web server can receive it properly. Just like the mailman routes your envelope from box, to truck, to plane, and eventually it shows up in the mailbox of who you address it to. So network addresses, if it's an IP version 4 address, this is like the area code and the telephone number of your telephone. You got the 3-digit in the United States, you got the 3-digit area code, and you got a 7-digit local part of the number. So in networking, there's a network prefix or network portion. That's the leftmost part of the address. So if you're in Fort Worth, well, before we had all these multiple area codes, because everybody in the 90s started getting cell phones and pagers and fax machines, and all of a sudden we ran out of numbers. We had to get more area codes. The leftmost portion of a network address typically corresponds to a particular company or a particular subdivision of a company. So we have a bank of addresses that are reserved for South Campus of TCC. The remaining digits identify the individual exact device on that network. Is it an employee workstation or a student workstation or a printer? What is it? So the host portion is like the individual extension number. The The network portion is like the area code for the entire device. So back in the 90s, before we had 5 different area codes, if you were in Fort Worth, you had an 817 area code. They didn't have these new area codes yet. So I knew if I dialed a known number and it was 817, well, it's a Fort Worth number and I want to pay a long distance charge for it. I'll just dial this number. If it was someone in Dallas, what did I have to do to call them? I had to dial 1214, the area code for Dallas, and then dial the Dallas number and I had to pay a toll charge for it, unless you had a metro line. So in networking, networks need to figure out if the device they're talking to is on their network or on another network. And the way they do that is they look at the network prefix. They look at it's the equivalent of an area code in the telephone system. Oh, look at this, guys, both have the same prefix, the 192.168.1. They must be, like in Fort Worth, we're in the same area code. We're both 817. I can talk to them directly. I don't have to dial one first and go to the long distance operator. So when devices are on the same network, they have the same network prefix. So on the data link layer, if they're on the same network, the two devices that talk to each other will learn each other's MAC address and send information back and forth to each through unicast one-to-one messages. They'll know each other's addresses. This is local addressing. Now, what if I'm talking to devices on another network? Well, I will learn the MAC address of my friendly neighborhood router, in this case, R1, and he will relay everything to all the other world, the universe of other devices to me. He's my friendly neighborhood router. He knows how to get to everywhere else in the world. So local addresses, MAC addresses, this A-AA and 11, that's 11. These are MAC addresses. And sometimes, since it's hexadecimal, you'll see the letters A, B, C, D, and F, because that's a characteristic of hexadecimal number notation. Those are the physical addresses of each one of those devices. The physical address is only locally significant on your individual network. So here's our little network right here. Here's our friendly neighborhood router. We only care about the MAC addresses of those devices. If I'm communicating with some of the network over here, I don't care about his MAC address. All I care about is my router's physical address, because that's the letter bag I have to drop the transmission into so it'll get delivered to the other networks. So in different networks, I don't care about their MAC addresses. All I care about is my default gateway's MAC address. He's my relay messenger to get any communication to any other parts of the networks. I will go through him. He'll get it for me. He's my gateway to get. We used to call them gateways. Now they're called routers. Then the routers will talk to each other using some sort of routing protocol, find the best path, get my packet over to the other network, and eventually the server will hear it and he'll send an answer back to me. And the whole process will take place again in reverse. So when source machine PC1 sends out a message, his MAC address is this AAAAA. He's PC1. That's his identity. That's his physical identity. The destination network is his friendly neighborhood router. His gateway is going to receive that information. And as it goes to through remaining hops to that server, the physical addresses will change, representing each of those physical networks. But his packet won't change. So allegory, if I take an envelope and I drop it into the mail system, do you get a message from me with a bunch of scrawled numbers on it indicating this physical journey that envelope took? No, you don't get that. You get the original unchanged envelope. So the browser will receive the original unchanged packet with the layer 3 network addresses that he needs to figure out who the destination address to send it back to. So layer 2 addresses changes from hop to hop. It's only locally significant on each one of those individual hops. The layer 3 addressing on the envelope remains the same, does not get changed. Crucial concept. So since data link addressing is local only, there will be a local source and destination only. If I want to transition to a next local network, it's going to pass through a router and it'll give it new layer 3 addresses. And then it'll go to the third network and it'll get a third set of new layer 2 addresses. So the first hop is completed, and now it's in the process of going through this point-to-point connection between one office and another office, maybe through at least data telephone line. And I'll get a new set of layer 2 addresses corresponding to this guy's physical number, physical MAC address, and this guy's physical MAC address. And then when I get to the third point of the network, I'll get this third links. This, in this case, the fifth and the sixth physical addresses will be added to these Ethernet layer, data link layer. Frames of information, as I said, back and forth. The original data, like the envelope in the mail, doesn't get altered. These numbers do not get altered. The information does not get altered. And finally, the receiving machine receives it, and the final destination, the layer 3 addressing remains exactly the same. Okay, hang loose 1 second here. Is the other one still going? Hold on, I'm going to stop and just to remind 1, 2, 3, 4, 5, 6. No. Share application, window. So just a reminder here again at the last that if you go to the Texas NetAcad career fair link at the bottom of my TCC Blackboard and click on that link, you'll get the screen where you can actually click on a link and enroll for a webinar, which will be on April the 15th at 12. Great way to get a gauge of the CCNA trained and certified people, what the job market is like in the Dallas-Fort Worth area. These are hiring employers that are going to be coming presenting at this, and they have been known to actually hire CCNA students that were real close to getting their CCNA or already gotten their CCNA. So the job market in Dallas-Fort Worth is pretty good for networking CCNA stuff. So check that out. Okay, I'm going to, hold on, I'm going to stop recording and click here.